Hello calculus fans. Today we take a look at section 11.6, which is our last section that deals with these convergence tests for series. So this one sort of picks up where 11.5 left off. And if you remember from 11.5, we had a couple of tests. So we had the comparison test, or sometimes called the direct comparison test, and the limit comparison test. Both of these depend on first making a guess about convergence, right? So we would talk about like long term, what do we think this series is going to behave like, then finding an appropriate series for comparison, both of which can sometimes be difficult. So in these cases, the next test can often be used since it works exclusively with terms of the given series. So it requires neither an initial guess about convergence nor an appropriate series for comparison. So it's kind of an easy test to use, and it's called the ratio test. And what we do is we take the limit of the nth term plus 1 of the series. We divide that by the nth term. We take the limit of that wrapped in absolute value, and if we get a number less than 1, then the series is absolutely convergent, and of course therefore convergent. If on the other hand we get a number greater than 1 or infinity, so in this case greater than 1, I'm going to say or infinity. If it goes to infinity, then the series is divergent. And the worst case scenario is if we take this limit and we get 1, then the ratio test is inconclusive. So if we get 1, it's inconclusive, which means we need to use another test. The little note here is that this test works well with factorials. So it's sort of a red flag. If you have a series that has factorials, right away just think ratio test. So factorials like n factorial, remember something like 3 factorial is just 3 times 2 times 1. We don't really see factorials a lot in calculus because factorials appear most of the time in discrete math courses like discrete math or maybe finite math or probability and statistics. Calculus typically doesn't have them, but they definitely show up in calculus when we have series. So when you see a factorial, right away you just think ratio test. Okay, and we've got an example here, and speaking of factorials, look at that. We've got this kind of strange looking series with a factorial up here, n to the nth power in the denominator. And they want us to test this for convergence or divergence. Well, right away, because I see a factorial right here, n factorial, I'm thinking ratio test. So the way it works is this. We take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Okay, so that's going to be the limit as n approaches infinity. Well, a sub n plus 1, basically this is a sub n right here, right? So wherever there's an n, I'm going to plug in n plus 1. So that means in the numerator, we're going to get n plus 1 factorial over n plus 1 raised to the n plus 1 divided by a sub n, which is n factorial over n to the n. We wrap both of these in absolute value. Now what we're going to always do from here is just, instead of dividing, we multiply by the reciprocal. So this pretty much happens every time you do this. So we're going to end up with a limit as n approaches infinity of n plus 1 factorial over n plus 1 raised to the n plus 1 times n to the n over n factorial, right? Wrapped in absolute value. So instead of dividing by this, we multiply by the reciprocal. You might notice that at this point we don't really need absolute values. Factorials are positive, so we don't really need these absolute values anymore. But also, when you have factorials, we get a lot of canceling. So n plus 1 factorial Okay, let me just quick review something. If I had 7 factorial, I know that is 7 times 6 times 5 times 4 times 3 times 2 times 1. So isn't that then 7 factorial the same as like 7 times 6 times 5 factorial? Right, we can do something like that. So n plus 1 factorial then, n plus 1 factorial is really just n plus 1 times n factorial, right? We could do it like this. N plus 1 factorial is just n plus 1 times n factorial, right? Because n factorial would be n times n minus 1 times n minus 2 times n minus 3. So the advantage of writing it this way is then we can get these to cancel. All right, so let me get this 7 factorial stuff out of here a second. So that n plus 1 factorial is just n plus 1 times n factorial. And then we can see that these, I'm going to just rewrite that. And now we can see that these n factorials will cancel. Right, so those are gone. So then what we get is the limit as n approaches infinity. So I'm going to have n plus 1. Again, I don't really need absolute values anymore at this point. N plus 1 to the n plus 1 times n to the n over 1, basically. And then we can work with this. This is really, basically there's just a lot of algebra here. We just have to kind of tweak this and see if we can get a limit that is not infinity over infinity, right? Because right now these are just infinities over infinities. But n plus 1 times n plus 1 to the n plus 1, isn't this thing, couldn't I write n plus 1 raised to the n plus 1? Couldn't I write that as n plus 1 time, or n plus 1, let's think of it to the 1, times n plus 1 to the n? Right, that's the same thing, right? Because here we would, if we multiplied these two together, we'd add the powers, 1 plus n plus 1. So n plus 1 to the 1, this is n plus 1 to the 1, so these actually cancel, right? So we could cancel the n plus 1 and the n plus 1 and just get the limit as n approaches infinity. So in the numerator, we're just going to have, because this would cancel, so we just get 1, right? This goes 1. So the numerator, we're just going to have n to the n. Right, when you multiply these fractions straight across, and down here we're going to have n plus 1 to the n. So you get n plus 1 to the n. Now we know how to deal with this. These are both raised to the same power, so we could just write this as the limit as n approaches infinity of n over n plus 1 to the n. Okay, now from here, this is not super easy to figure out the first time you see this, but this sort of thing will happen more than once when you have this sort of series. We're working with the ratio test. So once you see it once, and it's not too bad. It's just hard to figure out the first time. Okay, but what we can do here, because we basically have infinity over infinity raised to the infinity, but we can tweak this because algebraically, that is the same as the limit as n approaches infinity. I'm going to write it first, and then I'll talk about it. This is the same, right? Basically, what I want to do is I want to have one term on the bottom, or, one on the bottom and 2 on the top, because I can't really break this up, but I can break this up. So to do it, I can just take the reciprocal of this and put it under 1. This says 1 divided by this, which is the same as 1 times the reciprocal of this, which gets us right back here. But this denominator here, now I can write differently, because just off to the side here, n plus 1 to the n, we know that is n to the n plus 1 to the n, right? I can split those up because we just got one term in the denominator, and that's equal to 1 plus 1 over n. So when we have this, we can split it up like this, and then n over n is just 1. So we can work with this. We can't do that here. When there's two terms in the bottom, we can't split it up like that. So really what we've got here, this is the limit as n approaches infinity, 1 over 1 plus 1 over n. Okay, and now with this power, or this numerator of 1, we can write this way. We can say this is equal to the limit as n approaches infinity, 1 to the n over 1 plus 1 over n to the n. Right, we can break these up just like we just the opposite of here. They're both to the n power. We put them both together under to the n power. This is just the opposite of that. Right, so these are both to the n power, just that rule of exponents from algebra class. A over b to the n, it's a to the n over b to the n. We're just using that rule here. We're just going over here. But now this is the actual number 1. It's not a function approaching 1. It's just 1. So 1 to the n power, that's just 1. So I don't really even need this n. I'm just going to get rid of this n. 1 to the n is just 1. So this puts us here, and now we've got a number that you've probably seen in Calc 1 but may have not seen in a while. But when you take the limit here, this is a famous limit. 1 plus 1 over n to the n. So if you look at it, it's indeterminate form, because this is really a number approaching 1, and this is a number approaching infinity, but this is a famous one. That's equal to e. It's 1 over e. And you may remember that from Calc 1, but 1 over e is less than 1, right? This is less than 1. So according to the ratio test, since it's less than 1, this series is absolutely convergent and therefore convergent. So I'm going to talk about this e in a second here, but let's just finish this problem. So we can say, therefore, n equals 1 to infinity of n factorial over n to the n is well, let me say this a little quicker. I'm just going to say, so this series converges, and sometimes you'll say absolutely. Right, because by the ratio test it says it's absolutely convergent. So it just converges. The key is, what we're interested in is this converges. If you want to add it converges absolutely, you can. But mainly we just want to know that it converges. Okay, now back to this. In Calc 1, typically you'll see a couple of limits. You'll see the limit as n approaches infinity. 1 plus 1. Or actually in calculus it would probably be x. Let me replace this with x. This is e. This is the most common way to see this limit, but also you see sometimes like this limit as x approaches 0 of 1 plus x to the 1 over x equals e. This one is the most common. This one first came out of compound interest. So e first made an appearance in the world through compound interest a long time ago. And then it's just showed up in all kinds of seemingly unrelated places. But so you should have seen this at some point in Calc 1. So when you see it here, we just have to recognize, oh, this is e. This is e. So then we get 1 over e, which is less than 1. Okay, so that is how we could do that problem. E doesn't make an appearance in all of them, but what will happen with a lot of these, with the ratio test, the factorials, is you go through these cancellations. There's going to be a lot of cancellations like we did here, and then eventually you get an answer, and you just see if it's less than 1 or greater than 1, and worst case scenario, it equals 1, which again doesn't happen very often. Okay, then we've got one last test. The last test that we look at, which is called the root test. This one really doesn't come up very often, but it's nice to use when nth powers occur. Again, not very often. And this one isn't even listed in all college calculus textbooks anymore. But I know you guys wanted to get your money's worth, so I had to put it in here just in case. And there'll be one or two in the homework where we use this. But it's very similar to the ratio test. It has the same setup. What we're going to do is we're going to take the nth term a sub n, wrap it up in absolute values, and take the nth root. So usually you would do this if you've got a series that is raised to the nth power. So this one's kind of also sort of an easy one to see, because you have something raised to the nth power like this. See, there's n out here. Okay, so the results are very similar. If we end up getting a limit of 1, it's inconclusive, which means we need to use a different test. It doesn't happen all that often, but it could happen. So let's try this one. Okay, so we've tested the series. We basically can use this root test. We take the limit as n approaches infinity, and I'm going to take the nth root of the absolute value of a sub n. So that looks like you can take the nth root of this thing, right, wrapped up in absolute values. So we'll have the nth root, natural log of n to the n, raised to the nth power. We wrap up that in absolute values. And we will get from here the limit as n approaches infinity. Okay, so the nth root of the nth power, these will cancel, right? Like when you take the square root of a square, they cancel out. They're inverses of each other. So we end up with just the natural log of n over n. We don't need absolute values here because n is going to infinity, so there's no negatives here. So you have just natural log of n over n. So when we take this limit, we get infinity over infinity, right? Infinity over infinity means that we can use L'Hopital's rule. So I'm going to put a little equals here with an h. So then we take the derivative of each of these, and let's see, we get the limit as n approaches infinity of the derivative of natural log of n, would be 1 over n. The derivative of n is just 1. So this is the limit as n approaches infinity of 1 over n, which equals 0, which is less than 1. Therefore, our series from 1 to infinity, natural log of n over n raised to the n, converges absolutely. And again, all we're really looking for is that it converges. Technically, it's absolutely convergent. So that kind of wraps up all the tests that we'll be responsible for, which is basically all the tests that exist for the most part. And then there's a little extra here. So in section 11.7, it's just a bunch of series mixed together for practice. So we don't officially cover that section, but it's just a bunch of practice problems. But it does have a strategy that's pretty good. So when you get a chance, you may want to take a look at this strategy for testing series. And it just gives you some ideas about testing series, some ideas to make them a little easier. But what you should do when you work on these is just have that sheet with you. That sheet we filled out, a summary of available tests for convergence or divergence of infinite series. Just have that sheet with you when you're working on the homework or any test or anything like that, and they use that as a guide to walk through these and figure out whether the series converge or diverge. So now it is your turn to work on some homework, and as always, let me know if you have any questions.